I want to construct the Fourier series for this piecewise function. So what I want to do first is draw a quick picture of the graph. This first piece, x plus 1, is a line segment with a slope of 1 and a y-intercept of 1. So it looks like this. This next line segment has a y-intercept of 1 but a slope of -1. So it looks like this. Note that the graph is symmetric over the y-axis. So because it's symmetric over the y-axis, it is an even function. This is really handy for us. Even functions are ones for which b sub n, when I compute the terms for my Fourier series, are automatically 0. And instead of integrating from -L to L when I compute a sub 0, I can integrate from 0 to L of f of x dx. And instead of putting a 1 over L, I put 2 over L. I double my result. In a similar fashion, instead of integrating from -L to L for my cosine series term, my a sub n term, I do 0 to L of f of x cosine in pi x over L, once again doubling my result. So instead of having 1 over L, I'm going to have 2 over L in front of my integral here. Okay, so I'm going to integrate 2 over L. Note here that L is 1. There's L. So I have a sub 0 equals 2 over 1 integral from 0 to 1 of f of x. Now you might say, well, f of x is this weird gross piecewise function. It looks to be multiple pieces. But remember, we're only looking at the interval from 0 to 1. So I only need to consider this piece here, the 1 minus x. So I want to put 1 minus x dx here. I'm going to go ahead and integrate this guy. This is going to give me 2 times x minus x squared over 2. Plug in 1, plug in 0, find the difference, and when I do, I get 1 minus 1/2, which is 1/2, times 2 is 1. Okay, I have a0, now I need to find an. An is going to be 2 over 1, because L is 1, integral from 0 to 1 of 1 minus x cosine in pi x over L, and of course L again is 1, so I'm going to say divided by 1 here, dx. This integration is going to require integration by parts, but I'm going to use tabular integration. So in case you didn't know tabular integration or need a refresher on that, here's how tabular integration works. You put the polynomial piece here, you put the trig or exponential part here. So we have cosine of n pi x. You can say divided by 1, but obviously dividing by 1 doesn't change anything. Okay, so we've got the polynomial part here, the trig part goes here, and now I take the derivative of this column till I hit 0. The derivative of 1 minus x is -1. The derivative of -1 is 0. Now I can just stop there. For this column, you integrate. So the integral of cosine in pi x is sine in pi x over n pi. The integral of sine in pi x over n pi is negative cosine in pi x over n squared pi squared. Now we're not out of the woods yet. We're almost done with our integration by parts. The next step is to connect terms with upper left to bottom right. And by that I mean take this term and connect it with a line segment to one row down and the column over. I'm going to do the same thing with the -1. I'm going to connect this -1 to the negative cosine in pi x over n squared pi squared. And we have to do one last thing. Starting with a plus, we're going to label each segment with an alternating sign. So we do plus, then minus. If we had another segment, we'd label that with a plus, and so on. Our answer for the integration by parts is the product of these two terms without a sign change. So we're going to have equals 1 minus x sine n pi x all over n pi plus -1 times negative cosine n pi x over n squared pi squared with the sign change. So we have negative, 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 gives us negative cosine n pi x over n squared pi squared. I'm now going to evaluate this from 0 to 1, and don't forget I have a 2 over 1 sitting out in front, so I'm going to say this whole thing is going to be multiplied by a factor of 2. Okay, now I'm going to plug in x equals 1. When I do that, I get 2 times, open parentheses, 1 minus 1 is 0, 0 times anything is 0. I'm going to plug in 1, n times pi times 1 is n pi, so I get cosine of n pi, all divided by n squared pi squared, minus what I get when I plug in 0. When I plug in 0 here, I get 1 minus 0, which is 1, but sine of 0 is 0. And when I plug in 0 here, I get 0 times pi, or 0 times n pi is just 0. Cosine of 0 is 1. So I get 1 over n squared pi squared. Okay, I'm going to close this, and I'm going to clean this up a little bit. I want to identify that cosine of n pi. Let's remember that cosine of n pi is -1 to the n. So I'm going to replace this cosine of n pi by -1 to the n. So I'll have 2 times negative negative 1 to the n over n squared pi squared, and I'll have negative negative, so that'll end up being plus positive, 1 over n squared pi squared. I want to list out the first several terms of n just to see what this pattern is. So when I plug in n equals 1, I get negative 1 to the 1, which is negative 1, times negative 1, which is 1, plus 1 is 2, times 2 is 4 over 1 squared pi squared, because I plugged in n equals 1. So I get 4 over pi squared. That's what I get when I plug in n equals 1. When I plug in n equals 2, I get negative 1 squared, which is 1, times negative 1 is negative 1, but plus 1 is 0. So when I plug in n equals 2, I get 0. When I plug in n equals 3, negative 1 cubed is negative 1, times negative 1 is 1, plus 1 is 2, times 2 is 4, and in the bottom I get 3 squared, which is 9, so I get 9 pi squared. When I plug in n equals 4, I get 0. When I plug in n equals 5, I get 4 over 25 pi squared. Just noticing that the pattern is I'll always have a 4 in the numerator, and I always have an odd number squared in the denominator. So I have 1, 9, 25. Those are my odd numbers squared, along with a pi squared in my denominator. So I'm going to now go ahead and set up my Fourier series. Remember, the Fourier series form is going to be a naught divided by 2 plus summation a n cosine n pi x over L plus b n sine n pi x over L as well. Now we established that b sub n was automatically 0 because this was an even function. So I don't even need to worry about this term here. However, I do remember that a sub 0 was 1. So I get 1/2 plus summation from n equals 1 to infinity of a sub n. A sub n I found to be this magical form here. I've got 4 always in the numerator. I've got 1, 9, 25. Those are my odd numbers. Odd numbers are represented by 2n minus 1, and these are the odd numbers squared. I also have a pi squared down below. And now I'm going to go ahead and say cosine n pi x over L. Actually, I'm not going to say n pi x over L. I'm going to say 2n minus 1 times n pi x over L, because remember, my even term, n equals 2, and my n equals 4, those even terms are 0. So I actually don't want n pi x over L here. I just want 2n minus 1 pi x over 1, because I only want the odd number term, because the even number terms vanished. So this is the Fourier series for this piecewise function.